the start of a new day. A new shift for the factories. What shall we turn out today? A supersonic aircraft, maybe? A Sputnik or a spaceship? Anything is possible in this machine age. But as the wheels of industry start to turn, man calls for the one thing he cannot create himself. Energy, power. Since he first took a stick to lever a stone from his path, man has sought for power to help his own strength. Horsepower, steam power. And now today, electrical power. Striding across the country, the grid lines reach out from the generating stations, carrying energy undreamt of a few generations ago. In the control rooms of our power stations, engineers watch the heartbeats of industry, keeping the delicate balance between supply and demand. The supply comes from such generators as these 60-megawatt units, which are driven by turbines that draw their energy from steam. The steam is raised in great boilers that develop the tremendous pressures and temperatures needed for efficient operation of the modern turbine. And all this power derives from the combustion of coal, pulverized coal, which is burnt in these furnaces. This is where we in Britain have a problem. We can see a time when we shan't have enough of it. Millions of tons of coal have to be mined, transported, and processed for the production of electricity in the conventional power stations. Water power in small quantities and oil, which must be imported, were the only alternatives. That is until the world began to hear of Calder Hall. Opened in 1956, Calder Hall was the first evidence of the practicability of a new fuel which the world till then knew only as an agent of war. The energy of the atom had been released and controlled for man's advancement. The British government were convinced that this was the answer to our power problem. The race was on to provide new power plants using this nuclear fuel of the future. Whilst the electricity authorities searched for possible sites for future stations, the nuclear power plant company at Knutsford in Cheshire had been formed to prepare a design based on their member company's experience at Calder Hall. This design secured for them one of the first two contracts placed by an electricity authority with private industry. Bradwell. On the shore of the River Blackwater in Essex, they started to build in January 1957. By the way, don't look for any particular magic in a nuclear power station. They're using standard engineering techniques, but applying them to novel problems and new materials. That's why they formed the NPPC from several companies, each with its own background of experience relevant to their new problem. There's Railroad, for instance. They've been associated with switchgear for conventional power stations for many years. Some of the switchgear in a nuclear power station will bring special problems. And Railroad's experience will also be used to develop the mechanisms to control reactor output. Parsons, another company of the group, have been making turbines since their founder, Sir Charles Parsons, patented his reaction steam turbine in 1884. They will build the turbo generators for Bradwell. Their problem will be the efficient use of low-grade steam. The nuclear reactor cannot produce steam at the same temperatures as the fossil-powered boiler. Therefore, a greater volume must pass through the turbine to achieve the same power output. However, Parsons built the turbines for Calder Hall, so they've had practical experience of this problem already. Steam is something that will also concern Clark Chapman. They've been making steam-generating plants for many applications, and with Head Wrightson, will apply their experience to produce the best possible steam from the limited temperature in the gas leaving the reactor vessel. The design center of the NPPC was placed at Knutsford, close to the industrial headquarters of the United Kingdom Atomic Energy Authority. Several changes had been made on the Calder Hall design. Bradwell was optimized for power production with plutonium as a byproduct. To take full advantage of natural circulation in the coolant gas, the reactor vessel has been placed low in relation to the boilers. Bradwell is essentially a compact design. 2 reactor buildings and the turbine house in the foreground are the main features. The excavations are already well advanced. This neatness of layout makes for low cost. It also helps the site construction engineer. A building site, like a factory, can be more efficiently developed where there is unimpeded access to the working areas. Nearby, there was an old airstrip left over from the war. It's ideal for those who travel to the site by air. The NPPC's civil contracting is handled by McAlpine, who were pioneers of concrete work in Britain. They're highly mechanized, and their earth-moving machines and drag lines already cover the site. Here on the Essex coast, the low-lying areas are protected from high seas by a sea wall. To prevent any possibility of flooding of the plant should the sea wall give way, the spoil from the excavations is being used to build up the site above flood level. On many sites, the disposal of spoil would have meant additional expense. But in this case, they were able to turn it to advantage. The concrete for the foundation raft is made on a rather grand scale in these batch mixers. From here, it's carried by lorry about the site. Another method is to pump the mix through pipes laid about the site area. As you've probably realized, they need a lot of it. In order to avoid any differential movement between the boilers and the reactor vessel, the foundation takes the form of a concrete raft 200 feet by 100 feet, 9 foot thick. As you may imagine, such a block can't be poured at one time. The job has to be done in alternate sections. Quite apart from the foundations, quantities of high-density concrete will later be needed for the 9-foot-thick biological shield, which will surround each reactor. The reactor will stand directly upon the raft, but the boilers will be raised on stools at each end, leaving room underneath for the gas circulator. To place all these parts in position, Clark Chapman were given the job of erecting a Goliath crane with a lifting capacity of 200 tons. The first of its kind to be built to such a scale. Temporary buildings appear very early on any construction site. At Bradwell, in addition to the normal facilities, sheds are being built for storage of graphite blocks and for prefabrication of reactor sections, which the Goliath crane will then lift into place. This veritable skyhook provides a good, if precarious, view of the site. By just looking at the foundations of turbine house and reactor, one can hardly appreciate the immense amount of work going on behind the scenes. At present, the civil engineer almost has the site to himself. But elsewhere, there are the plant designers and the research people who support them. Crazy as this apparatus might seem, it's a useful piece of research for Bradwell. Tiny switches are being tested to destruction. And what about this? It's a selector valve used for detecting leaks of fission products from fuel cans. Here they're testing a control rod mechanism. To control the rate of the nuclear reaction, rods containing boron are inserted into the reactor core. The boron absorbs neutrons and slows down the fission process. In an emergency, certain of these rods can be dropped into the reactor core to effect an immediate shutdown. In Calder Hall, the reactor must be shut down every time for recharging with new fuel elements. But in a power station, we must refuel without interrupting the operation of the plant. Much of the work on this problem was undertaken by Strawn and Henshaw, who previously had been associated with coal handling equipment. Quite a change to come down to small grabs like this. Their particular problem was to perfect a technique whereby one standpipe on top of the reactor vessel could be used to charge several fuel channels. This is achieved by lowering the fuel element into a tube of which the lower section is hinged. The fuel element may then be positioned above any selected hole. In actual operation, one standpipe serves 34 fuel channels. The top of the standpipe will normally be sealed, the seal being manipulated in such a way that no gas escapes during the charging process. Spent fuel elements are removed by the same device. The fundamental research on fuel elements was the direct concern of Parsons. An efficient fuel can must have a high heat transfer coefficient, which has been achieved in Bradwell by a unique design of the can surface. Final proving tests on these elements were carried out at Knutsford in rigs, operating at full reactor working conditions. To study the consequences of any sudden change in the normal operation of the reactor, Parsons built a reactor simulator. An instrument like this can be of assistance in the design work on the control system. But when it comes to designing the support grid for the reactor core, then there's no substitute for physical tests on a model. Head Wrightson undertake this work on the support grid. They also carry out research on the transfer of heat from gas to steam in the boilers. Clark Chapman are responsible for the steam side of the boilers. They're developing the latest methods of automatic tube welding on this machine. The finned tubes being assembled here for Bradwell have been developed to transfer the heat from the coolant gas with the maximum possible efficiency. Ultrasonic testing techniques are used widely to ensure that none of the welds fail in service. In manufacture of the boiler shells, Head Wrightson use another ultrasonic test device on the raw plate before preparing the edges for welding. Then the plates are rolled to shape and checked for accuracy with a template. The circumference of the boiler shell is pierced by many parallel steam tubes, which call for close control of the drilling operation. The shell is assembled from ring sections on this jig. Already the great size of the finished article is evident. When they're welded up, the joints are X-rayed for any flaws. Transporting a vessel 87 foot long by 19 foot in diameter could be a problem. But Head Wrightson are on the River Tees at Thornaby, and they decided to seal the vessel and float it down to Bradwell by sea. The first of the seaborne boilers was expected at Bradwell in May 1958, and they were pressing on with the preparation of the blower house and the boiler foundations. This economy borer has been developed from oil drilling techniques. It's a speedy way of pile driving. Bore a hole and fill up with concrete. In the reactor building, the plinth that will support the reactor is nearing completion. This will have to support quite a weight. The reactor shell amounts to 1,000 tons. The graphite core, another 2,000 tons. And the fuel charge adds 250 tons, which makes a total of over 3,000. Wesso of Darlington are the company producing the reactor shell, and they have installed a new press to turn out the curved plates that will form the sphere. The press has a capacity of 4,500 tons, which is adequate for forming the 3-inch to 4-inch thick plates required on Bradwell. There is, however, ample margin for handling thicker plates, which may be required in the future. After they are formed, the plates are marked out for cutting by a shadow projection system. The cutting flame is carried on the end of an arm of the same radius as the finished vessel. The finished plates will then be welded together on site. It will be possible to carry the work to an advanced stage under reasonable conditions away from the building area, because the Goliath, with its 200-ton lift, can swing the complete rings, which make up the reactor vessel, into their final position. This crane is now a landmark. As the assembly has gone forward, the cranes that have been used to build it have been dwarfed by its size. It towers over the site area. 150 feet high, with a span of 167 feet, it can travel 550 feet from end to end of the reactor buildings. The frame of the turbine house is dwarfed beside the Goliath, this being the first of the buildings to take shape above ground level. This girder work is carried out by the last of the NPPC's member companies, Alexander Finlay of Motherwell. They have developed these box-section girders in connection with their work in conventional stations. On this machine, the 4 longitudinal welds can be carried out in 2 passes of the carriage. This gives a very even weld over the whole length. Back on site, the Spidermen perform their usual circus tricks as a cross member is swung into place. This turbine house will eventually accommodate 9 turbo generators, 6 machines providing London with power through the national grid, and 3 smaller units to drive the gas circulators. Nuclear energy is no longer a dream for the future. It is here with us today. From the heart of these reactor buildings that are rising above the countryside of Essex will come a new force, energy from the atom. Out of the years of research and design work has come the practical engineering fact. That is, Bradwell. The research will go on, and new designs will come forward, drawing all the time on the experience they are now gaining. We have come a long way in a short time, since the days when the future of Britain rested on coal. Today, the Nuclear Power Plant Company is helping to build a new future. A nation's development can be gauged by the power it can place in the hands of its people. Abundant, cheap power from stations such as Bradwell will give us the key to the future. For without power, there will be no future.